Okay, can everyone see my screen?
Yeah.
Good. And audio okay? I'll speak louder. Okay. Okay, so yeah, welcome. Session 2, the engineering design process is essentially the title, and we'll be starting with going over that process, but then really kind of laying some groundwork about what the beginning of that process looks like. And that'll really be the focus on systems and requirements. So yeah, start with introduction. We will go over, make sure everyone is up to speed with where we are with the repo on simulate in the HydraDX simulations, and then we'll kind of talk about where that fits in and for where we are right now and how we'll kind of expose going forward through the course of the next sets of lectures, so we kind of get the context of each decision and what parts are there and how they fit in with where we are. As I said, we'll kind of talk about the process in general and systems in general, kind of discuss a little bit more in detail about the Hydra system and really where the liquidity subsystem fits in. And then some thoughts about model-based system engineering, because we are building models and how that fits into this process. And then discussion about requirements and really about how we both determine and derive system goals through requirements and analysis of those requirements. And then we'll have you guys hopefully be able to apply that to a system. So introduction, and yeah, so here are the kind of the goals that we're looking for, about have some understanding about the engineering design process that we use at BlockScience, that we developed at BlockScience, I should say, and use, as well as then kind of go through some taxonomy about what we use in systems and systems engineering. You know, I'm sure some people have some deep understanding and know the taxonomy quite well, and others may be coming into it from essentially different points of view. But you know, there's a process there in terms of how we kind of define a system as well as determine requirements, which there is a process that we kind of iterate through, that the definition of that system itself can also help to define requirements if you're stuck on one end. So we'll get into that. We'll kind of see where essentially all the discussions that we're having about the hydro liquidity system subsystem and where that fits in within a larger system, whether it's the Hydra system or whether it's in a parallel world, or really the context within say the entire blockchain, or whether it's the entire economy, and then hopefully be able to apply some of these systems and requirements to a system or subsystem of your choosing. So yeah, so as far as, you're given the repo, really the goal right now was really just to make sure that you were, hopefully some people were able to clone or fork the repo, be able to run the notebook, but really, like, we didn't really want you to go further, didn't need you to go further than that at this stage. We will be kind of like peeling back the layers over the course of the next few weeks. And that way, ideally, by the end of that, then you will be like very comfortable with what is there, and also be very comfortable in either developing some parallel model to work with that, or some improvements within the model itself. So let's kind of, I don't know if everyone kind of has like some lay of the land for cadCAD, so kind of together some useful links for you guys and girls, hopefully. People. So CAD. Does everyone have a primer on cadCAD itself? I'm happy to answer anything that come up or have come up in discussions. Take that as a no or a yes. Yeah. So yeah, so cadCAD is an open source repo, which you can find here. You can also, and there you'll also get installation instructions, but you know, you can PyPI it, or so pip install pretty easily, or you can build from source if you like. We have many tutorials within this demos repo here. So, so one of the ones is the robot marbles. We also have a simpler one, but that'll kind of like step you through some of the successive elements of cadCAD that you can use. And then also we have a set of demonstrations will actually kind of, many of which will actually be pretty helpful for you guys even now as you're thinking about it. We have some both like a generic Uniswap or I should say a generic Uniswap styled AMM in that demo, as well as a ETH DAI Uniswap earlier digital twin. We're actually working on another one as well. And then there are some, if you go to the snippets, you'll find some small models and hacks. And then as far as we have, as far as like kind of like more community, we have cadCAD.org, and there is kind of the discourse. You'll find some older questions and answers there, and then we have Discord, and actually, and the start on Discord is a pretty helpful Notion document for getting up and running. And then we have our base model here. So again, we will spend a lot more time and really, like I said, successfully building upon this. So don't feel like if you're in the weeds right now, not understanding what is there, that won't be the case by the time we've gone through it. So yeah, so any questions about that? And there, like all the existing, we do have a lot more documentation already existing. We just, you know, are gonna build that in, just so everyone is good. Pause there for a sec. Just also wanted to open it up for anybody having trouble, but okay, so then let's dig into the engineering design process. And so we're going to look at essentially 3 different views of the process itself and how we apply it at BlockScience. But then, like I said, we're really the rest of the meat of this lecture will really be building the foundation about our thinking through this phase 1, kind of laying that foundation for that. So let's talk about these phases for a bit here. So we start with our phase 1 of system requirements, and sometimes this is like system and its requirements, depending on the problem at hand. So this often starts with it could start with a business problem. This could start with a technical problem. It could start with some definition. And again, and I'm going to talk through this kind of in the context of a client coming to us with a problem, because that's typically how we approach this. But there is often discussions and really trying to hammer down on exactly what the requirements of the system are or what the problem is. And so really kind of, you know, in simple terms, we sometimes call this being able to write down what the math problem is. And so like that actually takes work, right? Sometimes when someone has a problem, but they don't actually know what the problem is. And really being able to define that mathematically is part of this process. And within this, and we'll go into that as well as systems, but really trying to make some definitions around what the system is and how that fits in, both within some larger context, but also how the definition of the system can answer, be a part of the solution to that problem. So like I said, we'll discuss that quite a bit more in detail today. But then really stepping through these phases are also a little bit really dovetailing what the next series of lectures will kind of look like as well, because we are going to try to get you through this process, both in foundational, but with also in the world of the hydro liquidity system. So really, like from here, what we about at this stage, and you can see there's this overlap. So that's why I'm saying like about this stage. And then because this is engineering, we also have iterations. So like being aware of that. But roughly at this stage here, what we're often doing when we're defining the system, and you'll see if you've seen the syllabus for the next lectures, is we're often trying to couch that in terms of a generalized dynamic system, and that may be considered an economic game and maybe something else, but essentially we're defining the system within that context of that it's a generalized dynamic system. And so what that does is allows us to essentially write a mathematical specification, which is kind of like where we arrive around here, and then that specification allows us to build a cadCAD model, which you've already seen, but that kind of really gets us to like this stage here. So that's what I was saying. We won't jump too far ahead in that without knowing how we got there. But so like those are kind of like some of the key steps is the GDS system definition, the mathematical specification, the implementation of that as a model, which gets us here, and then we have the overlap on testing of that model. So both through simulation, through verification and validation, which we'll see on the next slide, and that kind of gets us hopefully to deployment. We're ready for deployment. So again, overlaps and iterations are part of the key. So kind of a different view of that process. So I won't go into quite as much, but we can kind of see some other thoughts about what is happening with this process. So we still have kind of the main ideas in these ovals that were roughly on the set of phases there, but some things that are different in this view that we want to that hopefully we see is that what we talk about here is like this V shape, and in systems engineering we use both the V shape, and we also think about these other V words of verification and validation, which are pretty important as well. So so what we're really trying to do is like start from kind of this global view or this broad view, and really as we work down through a design, we're breaking things into smaller pieces, into these subsystems. Ideally, we're breaking them down again through requirements and being able to write down smaller math problems that are more solvable, and working through the design down to its kind of like most specified version. And what we're doing here is making this both solvable, and by doing this we're also making it testable. So by going down, we can essentially now build a model. And so as we start to go back up this V, we can build the model, and now we kind of go back and we see like where those overlaps were on the phases before are now here, where you're building a model, you're testing out your both at the verification, so that the model actually says what the math said it should do. and that often may lead to a designer iteration about if that math was right, were their properties correct that we wanted to see? If not, then there needs to be a change in the design. As you go build up, then you're testing, say, like the entire system or an interaction between those systems, or say within components of within that subsystem. So that's integration testing. And again, that may, at that stage, that may uncover another set of properties that you say like didn't expect, or reveal say an inconsistency in your requirements, say that two things were against each other. Ideally not, but in real world that happens. And so then finally, as we go further up, now this is really getting into validation, where we're being able to do say more tests, say upon say a larger system, or say taking that subsystem and putting it within the context of a larger system, and be able to run more complex experiments, and try to say either derive or observe, say, emergent properties. Ideally, they would, there may be some notion of what those could be here, but that doesn't have to be the case either. But either way, like, so this is another view of that process, but this is also showing you ideally what the benefit would be of that process, that you would have these system properties actually be elucidated. Yeah, when you say test scripts, sorry, I can answer that, but yeah, we'll go through, like, yeah, so for the model itself, in this we'll be really going through exactly in the next lecture a lot more in detail what the constraints and requirements of the Hydra AMM liquidity subsystem are, and that's where we got to there. And yeah, in terms of with the tests that you're seeing right now, in that simulation is really verification tests, so they're here. But we do have tests for validation as well that we will expose later on as well. Does that answer that question? Okay. All right, and one last view about what this looks like. We have the design phase and the development phase. Again, one thing to notice is that really there's kind of this iteration loop in the design phase. There is going to be an iteration loop in the development phase as well. And so, being prepared for that or ready for that is expected and normal. And we can kind of see that this really kind of looks like the first two phases of that process on the design phase overlapping each other as we expect, or as we said. And so this kind of holds, but where we are essentially ideally from that business requirements, getting this formal definition, and then really what we're doing is really trying to revise around those formal definitions once they've actually been put into play, and we've implemented essentially the first set of, say, a mechanism or component, and done some testing. Then we're really refining what that looks like, how that's defined. And then as you move kind of further, and this is like what like phase 3 might look like from the BlockScience end of like where we might be honing in more directly on the cadCAD model, but also then, I mentioned like that ideally at that point, then you're ready for deployment. But what I actually mean by that is ready for deployment of now building, say like, you know, if it's Ethereum, say like building in Solidity, where there would be, you know, the almost like it's the transfer of say a Python cadCAD implementation of this system, and versus say like, you know, a blockchain implementation of that system. So therefore it would again be expected at that stage as well that there would be another say round of iterations, ideally much smaller and maybe say confined to data types or constraints on data types. Would be more the expected cases if we're talking about blockchain. But those things would still exist in that way. Any questions about the engineering design process from this very top level view? Let's see. Yeah, so so lastly,
I have a question. I was too slow pushing the mute button. Can you go back one step? For Hydra, I would be keen to learn more about where is Hydra? Is it still the design phase, what we are discussing here throughout the course? Or would you say, okay, we are actually in the development phase already?
No, we are in the design phase. We have gone through this loop, design loop, and we've actually gone through many times. And so we are at this, you know, essentially at the box where we have gone through this loop. Yeah, so we are at that stage where we have done validation and we have, you know, essentially we have a subsystem that does meet the business requirements here. So that's.
If I may add something, then yes, we are in design phase, but all of the other stuff that is not related to the specifics of the base pool itself are like already programmed. So we have like finished most of the development phase that is not related to the core of the AMM pool. And also we implemented like the first versions of the AMM, but it will probably like change internally because we are still like modeling the fees and making it better right now. So.
Yes. So go ahead.
With the dynamic fees, we would again enter the design phase for this particular subsystem or parameter, right?
Yes, exactly. So we have all of the other systems ready, and we can basically like it's all separate, like it's modules. So it's we can change some parameters in the development phase pretty easily. It's not like we will need to redesign everything from the scratch or recode everything from the scratch. It's just like we change some parameters. Maybe we add some storage needs to be added, but the framework is done.
Okay, cool.
And then just one question from the chat. Josu was asking if there's a schedule for when entering the deployment phase would be expected, or when deployment is expected.
So we are waiting for the Polkadot relay chain to open to parachains. There is no real date right now. Looks like the earliest will be November. And if that happens, we can just go with the current design iteration and just improve later. But I think like we'll have the complete design by then. So it's more waiting than than anything else.
I have a question about the parachain for Polkadot. Don't you like have to bid for that or something? Like, have you guys secured a parachain slot on Polkadot, or is this like, because I don't really maybe I don't really
Yes.
understand fully how it works. You have to
Yes, exactly.
you only to pay for it, yeah?
Yeah, exactly.
No,
We need
but-
to bid on the parachain.
Yeah, but it's done. The alternative and like the most reasonable use case how to do it is let community vote for it. It's called parachain crowd loans. So people are basically like lending to you their dots, but it's locked on Polkadot, so you don't have like direct access to them.
Okay, so you have to really hope that these people will vote for you to be able to get a parachain slot, right? And
Yes.
there's like probably lots of competing projects too.
Exactly. They basically need to see a value in your project for the like overall ecosystem, but also for their like missed opportunities from the staking, because they won't be able to stake during this like lease period. So they need to see like bigger potential in your incentives, in our incentives, rather than letting it staked.
Okay. And one more in the chat. Josie, would you like to speak up?
Is there an incentive for revising the core model, or like is there a scope for revision? Yes, if we find something like much better, then we're pretty open to revising. But I mean, like, we'll need to do something, right? So if the time comes, we'll have something ready, and then anything can happen because there is like a governance, and if we see something much better, then definitely.
But also anyone can like freely in their like free time or how much they want to commit for this research to test like different scenarios. And that was the assumption behind doing this like open initiative, that that more people can come up with more crazier or more uncommon scenarios, which actually like every time you can hardly predict the real market. So more scenarios, better for us, and bigger likelihood that someone would come up with better parameters or even like better model.
All right. Okay. Yeah, so last slide in this section about the engineering design process, and really this is just kind of touching on some of the kind of the core areas or the key pieces, or really even say skills. I wouldn't say these are I wouldn't say that these are disciplines, but they're, you know, essentially skills that we can that we apply as we go through this process. So yeah, so we have the systems engineering fundamentals, which I am hoping to deliver and hopefully have it come across today. And then, like I said, in the next section, in the next like essentially 2 lectures, really will be focused on the mathematical modeling. And as we build in the layer, like you've seen proof of existence of the computation model, but then also there's a lot more to that will be going over in the next few, and then you know towards the end, the last of the kind of the 6 where we are going to discuss about parameter selection under uncertainty. And so like where we actually do some different learning, we can apply learning models for essentially, we often at BlockScience, we don't often say that people want to start with optimization as say like a problem, as in their problem definition, right? And we often don't start with optimization because we need something to optimize against. And they're often competing value functions that may be optimizing, and say in the case of any AMM, right? You might say, oh, let's optimize liquidity fees, or sorry, transfer fees, let's say, while optimizing liquidity provider earnings, and those are always in balance, and it really is actually dependent on, say, like the actions, and that becomes of the actions that are themselves are occurring. So therefore, it becomes, you need something better to say, oh, well, this is the right fee, right? Like Uniswap optimized for 0.3%, right? Like, and we can be very sure that that is the absolute perfect number, or not, right? So we have a workflow around parameter selection. So in the case of, say, of the very bland fee scenario of, say, a percentage fee, you could even still apply this, but the hopes are that there will be a team or two or three that are applying a fee structure, or a dynamic fee, or some other fee mechanism, and that could still be used in the context of, say, even of this model, as where we could actually select, say a fee. And it doesn't have to be a fee value, right? It could be actually even a fee mechanism itself. But so, and then lastly, like, and this is, we have computer-aided governance. And so, this often doesn't come in directly in cadCAD, and say like it wouldn't come in directly in this model itself as a subsystem, but we'll see both today in Hydra, but also in general, how the governance subsystem, how that would actually interface with a liquidity subsystem. And again, this could actually be a place where say like decisions about fees lies actually outside of the direct system, or it could be baked or not baked into the model, but actually part of the subsystem itself. So those are also decisions that to be made, but also within the context of defining where this subsystem lies. Okay, so that is that portion. Okay, so then the next thing we'll discuss are like really some definitions around systems in general, and kind of going through a little kind of toy example about systems in general to get some ideas before discussing a little bit about Hydra. So let's see. So yeah, so we're gonna go through like about like kind of what is a system, and that is kind of purposely open-ended question. And so if we start with this example about like an industrial press, and so we have up here we're saying it's an industrial press system. Okay, so we're already using this word. So we have this press. It uses hydraulic pressure to push down and transfer forces to some workpiece, right? And so this could be used to form molds or tools. And ideally what's happening is that this is applying an even pressure or distributed pressure against the work area to push something down, putting things on top of other things. If you belong to that society. Old Monty Python reference. So anyway, the system itself or the hydraulic press has an operator, someone pushing the buttons. It has a user interface, the buttons themselves. It has controller software, so essentially the whether it's the controllers inside, whether they're you know, IC chips or whether they're something better, whether it's a PLC, etc. The controller hardware, so actually though that controller software telling the controller hardware whether to move up or down, and then the physical hardware itself, the hydraulic rams and cylinders. So the kind of the first open-ended part of this is, okay, so let's take another view of this, and then we're going to say, so where is the system? So we have another view of this this hydraulic press. You know, we have like the machine, which itself is like the physical controls, as well as the software behind the controls, the sets of actuators and sensors, the mechanism, and as well as the operator, essentially, and indicators, the operator controls and its indicators. And here's the operator, so essentially like there's where the interface lies. So so we have the machine and the problem world itself. And so, you know, the question is, okay, like what is the system? Where do we essentially draw the, in my experience, always drawing dotted lines, you know, to define a system and where that lies. So the first idea is, okay, so is this the system, essentially the combination of the controller software and hardware, and is that the system that we are looking to define? And so as I go through all of these, really the question is going to be a pretty important word that we're going to talk about is the context. So like, where does this fit in within the rest of the system? And so, you know, from here, from this point of view, really like what we're going to be going through is like, these are different subsystems of the system. But as we draw, every time we draw this kind of like teal box around something, you know, the thing to really look at is how many lines are entering or leaving that box, right? And that's a pretty important part about systems, is that, you know, any of those are interfaces, and they must be dealt with, and they must be dealt with explicitly and carefully. And so in this one view, say like, and this might be the view of the say the software subsystem and the software design team, right? This may be their view, and so therefore like this is their context. But you wouldn't want to give the software team necessarily this view, but to say, okay, like here's everything, and go build a software system. You know, that may, and I'm not talking about it from the view of, say, like turning things off, or that they can't handle that, but the things that are actually necessary in this system are purely to handle these interfaces, and do the correct inputs and outputs that come from each of those things. So okay, so then the kind of the more closed-in view, or the more local view, would be, say, purely just just the software itself. And again, this might be like another removing, essentially what we're doing is now removing a different set of interfaces, say, from both the actuators and the controls themselves. And now saying, okay, like all we are actually looking at as an input and output are the sensors and you know, turning those and having essentially the buttons or the indicators be aware through the sensors, and that may be the purview of this smaller subsystem. And then lastly, we have, well, not lastly, but like kind of the next view would be on the, essentially on, say, the more mechanical, so the hardware, as well as the interface, the operator interface, not the interface to the system itself. But we see here that the interface here is with the operator that's on the front end, as essentially being able to bring inputs into the system, as well as what the outputs of this system would be here. And we'll kind of go through, and then yeah, then finally, we have the control. Like really, this is essentially the interplay between the control system of the actuators and sensors with the software itself. And then this would be essentially the operator view of the system, where they're essentially just have this interface here, and this would really be the reflection of all those subsystems working together, and where this is the only interface, and the input and the output is here, and that is essentially performing correctly. Yeah, so essentially every time you make a slice, you have to be aware of those interfaces. I'll pause here. Some of the questions may be answered here, but are there any questions pertinent?
I have a question. Usually in such a problem, I would choose to slice it in the last way, where the system is the software and the hardware, and the interface is the interface to the human is the one that needs to be worried about the most, and everything else just naturally falls into place. So what is really the advantage of thinking differently from that?
Well, yeah, so good question. So a few things. What problems are you dealing with? Because so would be my first question back, right? Because in this case, like, I mean, in this scenario, number one, yeah, like that, yes, that's important, right? But like we have to consider all of them, because you actually want to design this, and both be able to specify the designs of these subsystems. And in this case, it's relatively simple, but in the case of, say, a much more of some complex system, it's not going to be this simple. So starting a problem with like, well, the operator needs to press the button and it works, is not necessarily a sufficient definition in order to solve the set of smaller defined problems that are also have to be integrated with each other.
I mean, the hardware itself has its own interface, and you don't have to think about it. You just have to, get your software to talk to this interface. And it's pretty, it's set in stone by the hardware manufacturer's interface, and you can't do anything about it. So what is there to think about?
So if I may, we were definitely thinking from the user's perspective first. So we try to do the model in a way that it brings advantage to users compared to other systems. But then if we are trying to model system that works in every case and every scenario, then we need to do exactly like this process. We need to engineer the system in a way that we know that it will not fall apart if user comes and does some arbitrary action. So that means we still think about it from user's perspective first, but then we try to model a set of mechanisms to do it. And then we try to use these principles to make sure it works.
So this is right. So you should still think about it in terms from the user's perspective first, but thinking this way basically provides a more robust system, right?
Yeah, and yeah, so kind of two other like points that I want to make about that is there are analogies, and we use this also in blockchain design, where there are existing pieces that say, and we'll talk about it later about requirements, like say that have to be taken as, say, a box that we can't touch, right? Say whether it's in this case parachain, right? Like it's something that there's all the things inherited, say, that are untouchable on Polkadot network. Well, like that is something that we have to account for here, right? And you might view that as your RAM and your piston, and you're not worried about it, right? But the interfaces absolutely matter, right? So that's one thought. And then the other thought is that we're also, in this case, we've already had that determination for us, right? But there are plenty of cases where you're not there yet, where you're saying, I'm not sure what RAM and cylinder I need yet. And so therefore I might actually, and in the old days, right, of say like before, in old assemblies, like where this whole was in one factory where they're actually, say, had a foundry and they were designing that RAM and the cylinder, that would be part of the process, right? And so being aware that in this case, like you're taking the view of like, oh, I'm just buying that and I'm plugging it in. But what if you needed something that was not already available and off the shelf as a piece of hardware? Then you would actually want to design that, and you would actually, then have a degree of freedom in that design choice about the interface itself. But like, I mean, your point about, like from that point of view about thinking about like, say, a piece of machinery that already exists, like that is also part of this process of where we have a box around that we essentially can't touch, but we still have to deal with their interfaces.
Yes, I used to think like all about that in the past, and then I realized that no matter how much I thought about it, when I actually sat down and coded it, I would it's like refactoring interfaces and APIs. Like when you actually you think you have a good design, but when you sit down, you realize, oh, actually it should be done like this way, and this only comes about through an iterative process. So I'm just wondering, like, how much improvement.
But it can actually kill the parameterization you did in the last state, I guess. So the stress test of that, or resilience of the 2 dimensions, I guess, is interesting.
Yeah, and so we'll certainly dig into that quite a bit when we come to it. And really, actually, it's pretty well. It's still dependent on on, say, like what the parameter set and how that parameter set actually is defined within this system as well, right?
Cool, thanks.
Thanks, Hendrik. And just a quick pace check. We have about 42 minutes left. So if we have some time, we can take more questions here, or we can keep marching through. What do you think, Barlin?
I have another.
Yeah.
So I've coded a couple of cadCAD models, and each time I always find them kind of I find the need to put the state variables within other state variables, sort of like a nested dictionary, either for programming, either for it's easier to access these things in the programming way, or also it just makes sense. So as not to have to juggle around too many variables in the dict. But then this leads to further complications, like how do you update a nested dict, a state variable nested dict, and then once you have a nested dict, then it really becomes tempting to convert it into a class and an object in the state, and then the state update functions gets like really complex. And then, so would you say this is an indication that you haven't that your system boundaries are too large, and you should like scope it down to a smaller system? Or is this normal?
No, I'd say it's normal. The short answer is normal. I totally understand every step of making those decisions because I've gone through that exact thing many times. I think it's more about the nature of the data structure than the let's say the complexity of your system. And the other thing that's actually that we'll see in a second here is totally normal is that all state variables are available if they are part of, so essentially if you're doing a global an update to a particular state variable, then all of the states, which is all of the state variables, are part of the available information to make that update. So that part is also completely expected.
Okay, thank you.
Good, you're welcome. Yes, I'll skip the last slide on system, and yes, so we'll just for case I think we'll be fine though, Peter. But yeah, so I'll talk about like some things about the Hydra system and getting into a little bit more about the liquidity subsystem itself, but really still at this like kind of very broad view, hopefully not too frustrating, that we're really still trying to take this system view of everything, and I promise we will dig in. So some things so some things here as we look at this crazy large picture of too many things happening, but not really, it's okay. But too small text. But so the reason is, so there's some reasons to show this. Number one is, again, like that a lot of times people may come to this and say like, come to this, meaning like come to this problem, and might say, okay, well, here it is, right? And now I'm just going to go and fix like, this piece wherever, say like fees. I'm sure fees are probably in here somewhere, right? And that's kind of like, where we are, say for some teams where they might be looking at, I'm going to fix like one piece of this, right? But let's also remember like some things which are like, okay, that we had to get to this point too, right? Like to develop this understanding about where everything lies and within its context to each other. And so some other points about here is like, so, this, again, like this would be something that you wouldn't necessarily start at this point here, right? To say, okay, like, well, here's my problem right here. I'm an operator. I want to press this button and I want this thing to come back out, right? Like you may have some definition around that, but then you're going to have many other sets of requirements that are going to be elucidated by the thing that you just said about like what you want to press and what you want to come back out. And then some other things about getting to the stage of being able to say write down that math problem is that you know, we might use, say, we use many different things to get to this point. So we use some mappings like this. We might use, say, you know, causal loop diagram, say, in that subsystem that you saw last week. We may use, say, an entity relationship diagram, you know, really kind of talking about, like, say, the data structure and, you know, what and how that is, you know, everywhere in any blockchain system, right? So like all of those things kind of help to get you to, you know, say like this, a point to draw this, say like a system map. So this was like, you know, kind of like, you know, I'm not zooming in, like kind of, because this was kind of like an early design, but to give you like some idea about like the different subsystems at play within say like a blockchain, right? And in this case for Hydra. And so this is a little bit better. And so don't, I would say like ignore a few things here, like that this wouldn't be like this wouldn't necessarily be like, say, like how a cadCAD model might operate. It could be, but it's like a little bit showing about like what possible mechanisms and what possible other parallel systems would exist. And again, this is like just kind of like this, some early mapping on this, but you know, we can kind of start to see that some things here, and don't worry, like we'll go to a smaller version of the liquidity, but we do see that there are other systems at play. So the security of the network, the parachain itself, which you already kind of touched on, an entire set of control processes, and like the treasury system itself, and we'll actually touch on that a little bit here, as well as governance, like as being a module. And so, you know, some things here that we'll touch on. So like both, you know, if certainly would kind of like not start ever with say trying to build a model that look like this, right? Like we would really start to tackle these individual subsystems, and even that is like still quite a bit to do. So firstly, you know, so yeah, definitely don't think about trying to do this as far as say modeling, but also this, you know, the other things here to see in this view are say like all the different places where some systems interact with each other quite a bit, and some less so. And so, you know, in here, like in this treasury, like there's a mint and a burn. Well, like there is in part of the liquidity subsystem, there is mint and burn that affects the treasury, right? So like that's a pretty important interface between whatever else happens with the treasury. And in this case, like, you know, so there could be other incentives, you know, or, you know, say inflation. And of course, like those things matter, like that, and that would be a flow, an interface with the liquidity system in terms of, say like, you know, like the quantity, the supply in existence, of course matters, but it also has its own effect on the supply. So like, you know, between minting and burning, that is occurring within the subsystem itself. So therefore, like that's a pretty important interface, and like a pretty like one that we would know of for liquidity. The other one, you know, would be that if governance, and so like kind of like, you know, one of the research questions might handle is like, okay, like, well, if the fee structure is say is part of say a governance module, or say, or some part of some centralized or, you know, or decentralized control module or a control surface over the liquidity subsystem, if that's where fees are determined, you know, like in some of your research to be, then of course like that has that has a direct effect on this liquidity subsystem, but it can still be handled as an interface with that subsystem itself. And whether that's static or dynamic, and those can happen. I'll go one step further. Do you want me to pause for questions, or I'll continue? Or
any questions on the last few diagrams, or I think we can probably just continue on.
Okay, so this is one started with most, and I'm drilling down to more palatable, and one more. This is still a lot, but so there's still one more simpler version to go. So I want to show you. So this is often we'll see versions of this here, and if you look through cadCAD, you've seen some different versions of what we kind of consider our cadCAD specification diagram. Majority of which I probably made, but so at this essentially and this also kind of hits on I think it was Andrew was saying about having that nested structure state. So we do, unless there's a restriction, say through let's say a permission blockchain or something where the information wasn't public, or whether it's hidden locally, then essentially the global state of the system is often in blockchains fair game for being used in a state update. And so again, so we kind of see that here, this top horizontal row is often the state of the system. Some things here, again, we're going to go into this more detail, but some things here is that in cadCAD, you can have global state variables, but then you can also have essentially sets of local state variables. So that's kind of what is happening here, and also kind of what you're seeing in also in that cadCAD model of say the agent class is really a set of local variables here, and then we would have say the global variables on Hydra itself, and then we have the second row is often the user actions, or it could also, if there was a control update, say for instance a parameter update, or some control function, that could also be in this layer. And then the third layer would actually be the state update, so the state function update, and where that now essentially is then just output as the new data into the new value, say, in the data structure itself. And so this essentially is what we might consider one time step, or one step through, and then this is just really our updated state, and then the next time step would go through this. But again, we'll go a lot more into the time steps. And so the last and simplest version of this, you can see here in this, which is also both the picture, but then one step above that is actually a demo, an open source demo of this Uniswap ETH DAI pair. And so here really just have 3 global states, and in that case, which is different than in our case, in the model that we have, where I did make the agents holdings their local state part of the system. In this case, in that model, what you'll see is actually all is really the agents events have actually just come in, but we actually don't have essentially an accounting for what happens to the agents themselves in that model. So essentially we just have agents coming in. They have knowledge of the global state of the system, and they know essentially give ETH and DAI gives them a price if they're swappers, or you know, if they're liquidity providers and then they have some knowledge about the value of their shares, and then they essentially perform one of the three Uniswap mechanisms, and that yields an updated version. But you know, again, like this is information flow, this is data flow about the action that triggers a state update. But they, you know, they can't, again, they don't do it directly. They can't say, okay, like I'm going to make, you know, make the state be this, right? Like they have to, all they can do is actually give tokens, right? And then you have that layer away from the direct control about this, the new state of the system. You can have a very good idea of what it will be, but you don't have the direct control because you're also not the only person, say, making that transaction, right? So you don't get to say, okay, the new state of the system will be this at the next block. Okay, so well, okay, and the last one in this section, we're doing pretty well, I think. So yeah, so like again, I wanted to kind of peel back layers in terms of what you guys have in your repo, and really like, you know, all we wanted to do right now is say, okay, like, you know, do you have it, does it work? And so, you know, really like what you have, like, but just by running the notebook is like, you just have, you know, essentially, I'm sure some people are very smart and have dug in, but, you know, at this stage, like, this is what's exposed to you right here, right? Is the notebook, and you know that there's an API call and there's results coming out, right? And then the entire system itself is shaded, right? Like that we haven't dug into that, but like we will go into great detail along the way. So that's the kind of one to put that in there too. So I can pause again here. I think we're doing okay. If there's any questions.
There hasn't been anything in the chat, but if you guys want to raise your hand or just jump in, feel free.
So basically, before you do any actual coding, you basically plan out the entire program with Lucidchart, right? I do. Like so the stages for me often are, well, there's many stages, but the mathematical specification is there. Like, so I would already have that. Then I would usually I'll start with Lucidchart to get my thinking around, you know, how the structure is going to be in rapid pace iterations. Sometimes I have to go back and update where my Lucidchart went to, right? Like, I mean, in terms of like where my model went to, but that certainly I might start there as I'm starting to think about the model. It helps me to think about, you know, what data structures exist, and, you know, make sure we're not missing anything. It's really like, you know, part of that is an iteration between the mathematical specification and writing the model. And so like by doing that exercise, that helps to say catch anything along the way, but also helps to describe what's happening. Yeah, great. Thank you. Good. Yeah, so I think we're doing pretty well. Do we stop, like, when how am I doing, Peter, in terms of like when do we try to
yeah, you're doing fine on time. We have until the top of the hour.
All right, so yeah, so a couple two small section on model-based systems engineering, just some thoughts. Essentially everything we saw before is like really from the systems engineering world, and there's a couple extra things to consider when we drill down into this model-based system engineering, essentially using a model in that loop, in that design loop. And so, like, you know, some ideas here, like on, you know, and this isn't to slight systems engineers versus model-based systems engineers or anything like that. But, you know, like a lot of times, like a systems engineer may feel as like almost like a referee, and where everything, like where all these things are happening, and they're just really kind of to try to calm things down, or have some sense of control over what's happening in the context of, say, like a design and build environment here. And essentially like what we're doing is like taking this, and we're also saying, okay, like, well, by having models in place and using models to say to run experiments, or just even provide answers. And so it could be a model with a set of models sometimes, but then they can handle questions about say, like, from people about, oh, I want to do this, what happens, or how come it does this when I do that, versus, hey, what if I put these things together? Do they work correctly as intended, as say two systems came together? So that would be like, testing the systems and integration, versus like, say, the people actually building the code and saying, oh, well, actually that didn't work, here's why. So like, it gives you the ability to say, to answer those questions, both from making a better design to going back to like that deployment phase, as well as, say, answering this, being able to build that design and test. So one thought about that. And then the other part of this section to also consider is like, don't forget like that we sometimes lose sight on the fact of in blockchain is like, oh, well, like everything's there. We can do, we have information about everything. So therefore we don't need to make any assumptions, right? And we can just build the world, right? But if we actually want to design the world, then we do have to say, make some limits, make some assumptions. And then there are the right places to say, like, deploy versions of that designer's model into a system, say like a test net, and see what happens, right? Or versions of where we can use the model, say, and hand over, say, like a governance control surface where they can start to make predictions about what's happening, or say like fraud detection, etc. So we can have different views and really even different models depending on what the problem is at hand. So like we're here, right? But we did essentially there's the natural to say, okay, like, well, let's put in the real data and see what happens, and that's okay. Like that's the intention as well. But just be aware of like what are you testing when you bring in real data? Are you testing against behaviors? Are you stress testing a mechanism? What are those things that you're doing? So so you can instead make assumptions about what could happen here and bring them in and test against the model before going. And then of course at some point, if it's built, it will be tested. But so you can still iteratively make those both assumptions and then relax those assumptions as you go through the process. Okay. All right. So let's see. Yeah. So just I think I'm doing pretty good. So yeah. So requirements. So one of the things, and like, so this will almost be like a little bit of kickoff for where we go. And like, well, I'll say, like, we already got a little taste of this of requirements in the previous lecture, and we're going to see more of it again. So we really like kind of dug in. And so when I'm saying requirements, this is actually like really like the system goals, right? And so we're going to talk about just a little bit about how we get there. So we kind of saw a little bit about how we got there in the previous lecture, but like here, like we're kind of taking a step back and say, okay, like, well, how did we get there, or what could you do, say, to pose the question or write down the question at hand. And so when we're talking about requirements, let's say like taking in those kind of those business business decisions or business desires, and trying to say, okay, like essentially both classify whether those become requirements as part of the system, whether they're part of certain subsystems, whether they are actually just we'll talk of whether they're you know, like part of the operation itself. So you know, some things to think about here is that when you're doing this, the design itself, like that the specification of those requirements shouldn't say, okay, like, well, it shouldn't have to be that here's a requirement, therefore I have to do it this way. Right? Like it's still just, it's a requirement of the system. And yeah, there's places where that's going to mean that, oh, like that it has to be implemented, you know, because of where it is, but those aren't necessarily like, say, a requirement of the system. That would be I'll talk in the next slide. We'll talk about like essentially like a lower level requirement about that system itself. But you know, really we're talking about is like, you know, at this stage that you need to be able to, that the requirement is really just like, what should it do essentially, like, or like what should a goal of it be, I should say, not the other way around. And so, you know, like also like, you know, the caveat here and is, you know, like the temptation to say, oh, well, here's this thing they wanted to do this. Oh, okay, that means like, oh, just do like, you know, log of x divided by, you know, e to the y squared or whatever, you know, some mathematical algorithm. But, you know, really like, again, you may be if you go there already, then like you may not be having the context about how that would affect other systems, let's say, in this view. So like you could be solving a small problem, but you wouldn't be solving necessarily for a system goal. And then yeah, some other things here about the system requirements is there is often translation work that we have to do, get everyone on the same page. And so like, you know, a lot of times for us, what we might do is we might build a glossary, we might build, we often build, say, like user taxonomies where we define user roles. That helps to kind of bring out what the operational requirements will be. We might build, say, like we do like a value flow taxonomy, and that really helps us to build out, say, like the stock and flow diagrams, or helps us to start thinking about, say, like a conservation equation, or I mean, like conservation principles, not equation, we wouldn't be there yet. But either way, like that part of that is to actually define those system goals in a way that everyone understands, and ideally, you know, universally. So that may mean needing more definition around those requirements. So some other thoughts, like, you know, some details, again, like going further into, say, like, oh, like, well, if, you know, saying like, oh, well, if I do A, I expect, you know, some very specific value, but that wouldn't necessarily be part of like a user test. It might be like some acceptance criteria, but it wouldn't be like something that would actually be part of a system test. And, you know, going back to the whole iterative process, and even, you know, I think, you know, there are places where, you know, like heard earlier in the lecture about, like, you know, Jakob said, like, well, there are things that we could do later. Well, like that doesn't, again, like it shouldn't necessarily change like what the requirements are of the system. Again, the system goals, but, you know, so like those can stay the same ideally if we've essentially written them down correctly and essentially everyone is in agreement, then better improvements don't necessarily mean that there's a change in what was already in the requirements themselves. It just may be an improvement in the design in one place in the design of the entire system. Yeah, so quickly, it says, probably should have put this slide before the other one because I was trying to not say words like operational and functional, but so be aware as you're hearing things, as you're hearing say, oh, well, we want a user to do this or that, then, just keep in mind that may not be what the system has to do, right? That may be that's going to be like an operational requirement in terms of what the system has to do, but it doesn't actually mean that the function itself of the system does that, right? It does something else. It may be taking that input and returning an output to the operator, but there would be, say, layers or sets of functions below that, like within, say, mechanisms that would make up your functional requirements. And some of these others, this is essentially from systems engineering, which from the military design workflow. So some of these, but I do like to have these here because think about just some thoughts about performance. Do you Uniswap or say any blockchain, is it always working? Do you always say Uniswap, do you always get the price that you wanted when you put in some tokens? It depends, right? You don't know, depend on activity. Some technical needs as you're going through some design, and then we have essentially these second level kind of derived and allocated, where they're coming in from say within a system. So the allocated ones that may be say for a liquidity subsystem that's existing on Polkadot, then that's where we would say, okay, what do we have that is not really changeable for the system. So it's just quickly, it's kind of similar ideas about the iteration on the design loop, but again, this may be a process in terms of saying, okay, when you said you wanted this to do that, did you really mean that, or did you mean something that was actually higher up, that it wasn't maybe. Oftentimes we might need to go higher, right? Say oh well, no, I didn't mean that it needed to be if I got X, I got Y. It meant that that this whole system needs to work where most of the time, say, people got X for Y, so those sorts of ideas, as you're kind of working through requirements, and again, when you're doing that, this is really just another kind of set of words around really what we do as a mathematical specification, and putting together that mathematical specification as an instance in cadCAD is really kind of this design loop. But again, this is really just borrowed from the Department of Defense about systems engineering. So just in different words, but really kind of those same ideas about loops. But this is the point here is to remember that there can still be a back and forth and iteration on what the actual requirements of the system should be. All right, and then so last up, what we were thinking about for taking in or trying to apply some of the systems thinking to whether you can do your own something that your own discipline, whether you're thinking about something, say any other system that you feel you could take on. You could take on essentially some first pass on Hydra subsystem, which are fairly generic in terms of other, you know, like any other blockchain that would have, okay, like here's a potential governance system or a control system, etc. You know, those aren't you know, especially unique, or say like another system that could potentially interface or have an implication on the hydro liquidity system. Say like, you know, there's an asset in the liquidity system and what's going on with that asset. Like, well, you know, if that's a digital asset, what's its system in terms of like how its value is created or even signaled, and you know, kind of from here, like what the focus should be are really like three things. Is just really like, I'm not saying like go and design we're not talking about designing a system. All we're talking about defining. So here it's just saying, okay, like where does the box around that lie, you know, and you know, even if it means drawing it, it means drawing it, right? Like it could be as simple as drawing it and say, okay, like I know there's say like, you know, Bitcoin, and there it is, there's a box around it, right? Or, you know, or it's, you could use a physical system, here's a boiler, you know, and drawing a definition around it where you're really just saying, okay, like what is in that box? Again, we're not designing it, but specifying like what's its interfaces, you know, what can come in and what can come out, and then describe like, what are the requirements? What is the goal of what is in that box? And like really like those three things are, you know, get you kind of thinking about this, and then both, you know, these problems in general of how we do them, but then it'll all tie back in to Hydra specifically. And that's, I think, about it. So that's what I have. So we have 5 minutes.
Yeah, just have a few more minutes left if there are any questions about this.
Yes, I had questions about the slide where we discussed the model-based system engineering versus traditional system engineering. So if you could go to that. Yeah. So the general difference in these two scenarios is on the left, we're just describing the relationship between different systems, and on right, it's defining different thresholds and requirements and goals and using that to simulate. So just could you go through what are the like key differences? Are these just having different sort of state variables and values to simulate the system? So yeah, I just had some doubts about that.
Yeah, so I mean, the first key difference is that you actually have a model that you're actually using here. So whereas like you know, in say traditional systems engineering, that the idea would be that they wouldn't necessarily have a model. Like they would, you know, essentially they would have, say, process models, they'd have documentation, like that like the traditional systems engineer from, like, again, kind of coming from, you can see like this one's from NASA, so like from JPL, where they're building, you know, that this is actually specifically for building like a rover, but you know, like that traditional setting was in the absence of a model, where they said, okay, here is the process, and here is the test book, right, for like testing this one thing. And you know, and we see that in evidence, right? Like if you watch a launch, right, like the checks and the series of checks, they're going through, you know, these highly documented test books, but it was really like, it was that traditional role was a highly like documentation heavy role, as well as coordination. And so like on the right, it's really about like, okay, that using, it's not replacing, say like a systems engineer, but it's essentially using a system model to deal with the interfaces of all the questions that the scientists or the people building subsystems would say like, oh, well, what about this and what about that? And so it just is really about using that to help in coordination and answer questions.
But in reality, that means operations and assemblies and tests and systems must all know how to change and the system model. And the reality is that not all of them know how to program. So actually in the middle of them, there's actually the programmer, and that like they would all have to go through this programmer to modify the system model, right?
No, I don't agree with that, because what you have, like, I mean, you have a model where you know you're clicking run and it runs, right? But like, but we have models where we have interfaces where like for operations that where there's a changing like, and that's really where we put say like parameters at a very accessible level where they could say like, oh, like I'm just going to change one value and press run. I'm going to change phi from 0.3 to 0.4. And that's like, those are like, that's the operations, right? Like that's where that level of testing would be versus say like building the design, like we're actually doing the design. Like, yeah, that's, you know, that's inside this, right? Whereas like the operations like would be essentially outside. They're not like touching that. They're not in the model. They're doing an experiment on the model, or I should say a simulation on the model.
Okay, so you mean that operations would just change a cadCAD param and run the simulation, and that would actually be like just one of the submodels, like power model or thermal model or mechanical model.
Yeah, and depending on the structure, like, and in this case, it would be, well, you know, yeah, in this case, it was like the analogy to like say liquidity, yeah, like it would be the liquidity subsystem, right? If they change the field.
Cool. Awesome. Great question. Thanks for that. And then just before, since we just hit the top of the hour, before we all head out, I wanted to circle back to the last slide that you had about drawing subsystems, defining subsystems. Is this something that the group should take on for homework or as an exercise? Was that the suggestion?
Mm-hmm. Yeah.
Cool.
And it could be individual if you want to team up. Like I said, if you have strong feelings, you know, wherever your feelings lie, I think is fine. But it's really just, you know, going through that exercise about thinking about what's in it, you know, thinking about what's in something and what's outside of it. And, you know, ideally, you know, by doing that, like those three things, then you've got some sense about like, oh, like how would I go and design the thing inside that isn't inside of that? But, you know, again, without having to do that.
Cool. And the starting point is the overall Hydra system, one of the charts you showed, or any system in general.
Yeah, that could be one of the starting points. And I would take it as like almost a name only, or almost in, you know, like at its most at its least granularity. Cool.
Awesome. Then yeah, we can put that together. I'll mention the homework to the folks who had to drop out of it early too in the Discord. So all right. Then does that cover everything from your side, Barlin?
Yes.
Cool. Then thanks to everyone for all the questions today.
Yeah, really good questions.
Yeah.
Just
awesome.
one more thing, if you have a couple of minutes, Matthew. I wanted to like it was a very general question. The difference between system design versus system engineering is system design just mapping out the different relationships between actors, and engineering actually mapping out the constraints and the requirements and actually mathematical models. So what's from your perspective the difference between design and engineering, if you could?
Yeah, I think the engineering, like if you like kind of take that traditional systems engineer, there's it's almost like more of managing the iterations over the design, which also includes managing in that setting, like the different sets of stakeholders. And so like that's part of this, you know, like we're talking about like a fairly nuanced, that versus like a system designer might be saying, okay, like, well, here's everything, and here's how I view the world, right? But yeah, kind of like managing the engineering process. I would say that's the systems engineer.
Got it. Thank you. Great session, Matthew. Great session. Thank you, everyone.
Yeah.
Awesome. And thanks for the questions, Amanjot. Cool. All right, then I think that's everything. We can wrap up for today. And like I said in the chat, the recording will be available in the next few hours. I'll follow up in Discord with a quick summary of the links, and the slides will upload as well. So cool. Then yeah, just the last reminder is the next session will be on Tuesday, 4 p.m. CET, I believe is the time. And we will get into the hack and share session. So should be exciting.
Great.
Awesome.
Thank you.
Thanks again, Barlin.
Yeah, thank
We'll see
you.
everyone
Thanks,
next week.
everyone.
Yeah, everyone, that was fun.
See you next week, Tuesday.